Taklamakan lies in haze. Dunes rise like frozen waves around a desert long thought doomed to silence. Yet beneath this stillness, change had begun, ready to reshape surface and depth, showing how a wild land became an engineered haven for carbon and life. The desert that embodied silence. For centuries, the Taklamakan Desert sprawled so vast and harsh that travelers called it a border between worlds, not a mere place. Dunes, shaped by constant winds, slid on, still silently erasing roads, burying villages, driving wandering sands toward oases that fed the Tarim riverbanks. Scientists studying the area saw a biological void, lacking ecological resilience, yet noticed clues of an elusive process at work beyond human perception. As desert-edge communities fought encroachment with makeshift barriers and hard seasonal work, researchers questioned unexplained shortfalls that sometimes appeared in atmospheric carbon readings in western China. These anomalies hinted that the desert's silence concealed more than nothingness, suggesting a hidden mechanism influencing global carbon cycles in a way no model could yet fully explain. Through the 20th and 21st centuries, desertification grew urgent, pulling leaders, hydrologists, ecologists into talks on climate instability and arid spread. Their investigations revealed that the Taklamakan was not just advancing across the landscape, but interacting with it through dynamics far more complex than surface observations suggested. This realization launched research that later revealed the desert itself helps regulate global carbon levels. Hidden ocean, the missing carbon. When researchers looked beneath the dunes, they found an underground world larger, busier than imagined. Tarim Basin hosts one of Earth's largest hypersaline aquifers, a mineral-rich flow through deep rock layers that absorbs atmospheric carbon drawn down by meltwater from mountains as it sinks. The water acts like a pressurized gas solution, efficiently dissolving CO2 and carrying it into isolated cavities kilometers below ground. Salt reservoirs, isolated from biology, enable reactions converting dissolved carbon into stable carbonate minerals. Over millennia, this mechanism stored hidden carbon, and scientists never truly gauged how dynamic the system was. Recent geochemical studies revealed that mineralization in these aquifers can occur far more rapidly than previous estimates suggested, with some areas capable of converting dissolved carbon into solid carbonate in just a few years. This accelerated transformation challenges long-held assumptions about the natural pace of sequestration, demonstrating that deserts like the Taklamakan have the capacity to lock away carbon on timescales relevant to contemporary climate strategies. This discovery led to a reframing of the basin not as an inert geological formation, but as a functioning carbon engine operating silently beneath one of Earth's harshest environments. As these findings gained international attention, they opened new lines of inquiry into the relationship between surface conditions and subsurface sequestration. Scientists began to investigate how moisture pulses, groundwater flow patterns, and seasonal temperature gradients influenced the depth and rate of carbon migration through the basin. Their research revealed an underground system thriving without life, yet tied to surface climate change, a natural prelude to human actions soon reshaping the desert's edge. Engineering a forest against the sand. Before the Taklamakan's underground carbon vault was fully understood, China already launched an ambitious experiment along the desert's shifting edge. In 1978, planners launched the 3 North Shelter Belt to slow desertification by building a continuous ecological barrier across vast northern lands. What started as defense grew over decades into a massive environmental engineering feat for humanity, ending in 2024 as the last gap closed in a 3,046 km green ring around the Taklamakan. This achievement represented not just a symbolic milestone, but the consolidation of a landscape-scale intervention that profoundly altered the relationship between the desert and its surrounding ecosystems. Building a forest in a dry, salty region took trials with species that withstand conditions deadly to most plants. Foresters chose tough species: Euphrates poplar, a desert tree tolerating heavy salinity, and tamarisk, deep-rooted shrub reaching scarce groundwater in arid zones. Over time, these species formed a hardy front line, anchoring dunes, cutting erosion, creating microhabitats in barren areas. Satellites with solar-induced fluorescence sensors later saw measurable drops in atmospheric carbon along the desert fringe, visually confirming this engineered forest was absorbing carbon into growing biomass. Green Ring expansion turned the region into a lively eco-corridor where sand, plants, and climate began interacting anew. What was once perceived as an unchangeable wasteland gradually evolved into a managed system, capable of supporting life while shielding nearby communities from the desert's advance. This turning point set the stage for the project's next phase, where technology and human participation would amplify the forest's reach beyond traditional ecological boundaries. Gamification of ecology. As the Green Ring expanded, its maintenance demanded levels of precision and endurance far beyond what seasonal crews could reliably provide. The planting window in the Taklamakan remained extremely narrow, with only a brief period each spring when soil temperature, moisture levels, and wind conditions aligned just enough for young shoots to survive. To meet these constraints, engineers deployed autonomous reforestation robots with LiDAR sensors, onboard irrigation, and machine learning models, spotting ideal microsites amid shifting, unstable dunes. These robotic teams moved methodically across the landscape, planting thousands of saplings a day while adapting their techniques to shifting terrain and real-time moisture readings. Their steady precision raised seedling survival, letting the forests spread faster than humans alone. As tech advanced, public action arose unexpectedly via a mobile app, making the environmental protection a daily habit. The Ant Forest app incentivized users to accumulate virtual green energy by adopting low-carbon behaviors like walking, cycling, or using public transit. Once enough energy was earned, the app triggered the planting of a real tree in the desert, connecting individual urban choices to tangible ecological outcomes hundreds of miles away. This approach built collective ownership and shared drive, showing behavioral nudges can boost impact of large-scale ecological engineering. Together, automation and civic engagement shaped an evolving restoration model where tech policy and personal action converged to sustain infrastructure near desert. Albedo paradox, the water dilemma. As the forest matured along the Taklamakan's perimeter, Researchers began analyzing how this massive transformation was altering the region's energy balance and hydrological functions. Desert sand naturally reflects much incoming sunlight, forming high albedo ground that reduces heat uptake. Dense vegetation absorbs more sun, prompting, could big greening unintentionally warm nearby air? Early models said more evapotranspiration from millions of trees could offset this by releasing cooling moisture. But scientists quickly realized this delicate balance depended heavily on the sustainable availability of water. Without consistent groundwater recharge, the very trees responsible for cooling could weaken, darken, and eventually die, leaving behind heat-absorbing biomass that could amplify regional temperatures. The water sustaining these plantings comes primarily from glacier-fed rivers flowing from the Kunlun and Tian Shan mountains, making the entire system vulnerable to shifts in seasonal melt cycles. Climate projections indicate that accelerating glacial retreat could reduce river flows in the coming decades, raising concerns that the Green Ring could outgrow its hydrological carrying capacity. Ecologists warn plant stress could turn this ring from carbon sink to source, especially if many trees decline together. These risks temper the success story, showing even bold eco-engineering projects face limits from climate swings and resource rivalry. That tension between gain and risk pushed leaders to rethink long-term management, enabling a geopolitical view linking environmental repair and regional stability. Human-made climate border politics. As China refined its approach to desert stabilization, the Green Ring began to influence diplomacy in ways few had anticipated. The country's rapid shift from a major industrial emitter to an environmental innovator transformed global perceptions, framing its desert reclamation strategies as exportable tools for regions facing advancing sands. Great Green Wall nations and some Middle East states adopted Chinese-style dune stabilization, forming partnerships linking ecological restoration, infrastructure, and technology support. These partnerships boosted China's influence, expanding its role in adaptation policy. Yet the project again reignited debate on water resources, especially glacier-fed rivers sustaining both forests and downstream farms. Neighboring regions questioned long-term water use if expansion continues, sparking talks on cross-border water rights and ecological responsibility. Taklamakan's transformation, once an isolated national project, is now a case study showing environmental engineering shapes politics and strategy. This geopolitical shift recast the desert as frontier where climate action, regional diplomacy, and national aims meet, beyond surrounding forests. Along the shifting edge of the Taklamakan, a desert once defined by silence now reflects humanity's capacity to shape its future by uniting hidden geology with deliberate design. Let this story spark curiosity, inspire learning, and strengthen commitment to projects protecting fragile landscapes and Earth.